Well, good morning. We are going to do really like three major things today that just sort of continue the flow of the series and starting where we can use them to answer questions. So I want to start with the simplest of all, and that's going back to the geometric series. So if I have something of the form, and I'm going to do the most basic version. So you say, but what about the A1? Think of factoring the A1 out of the problem. In other words, I just want the part with the R. Remember, we say A1 plus A1R plus A1R squared. So if I factor the A1 out of the problem, and I'm just looking at this, okay, we'd say this is of the following form. We can write it like this. You notice I now started at 0. Before we were starting at 1 and writing it as n minus 1. Now if I start at 0, I can write it as n. And doing a quick check, it's the same thing. If I have a lead coefficient of A1, I'm saying factor that out of the problem. We know that this is equal to 1 over 1 minus R when is this equal to 1 over 1 minus R?
When it's for all numbers
It's converging.
larger than
When does this equal this? Is it always equal to this? If R is a large number, then this is going infinitely large. It's probably not equal to that. So
It's only if R is less than 1.
if the absolute value of R is less than 1, yeah, that's kind of huge. This is equal to this if this is true. So let's start with that statement right there. So here's what I want to do. If I have a quotient and I can make my quotient look like this, then I can write it like this. And here's what I mean. Let's suppose I had something like, we'll keep it really simple. I have something, let's say 4 minus x, and I would like to write this as a sum. Get rid of this. I would like to write this as a summation. Well, how the heck can I write this as a summation? Can I make this look like this? Oh, yeah, but I got a 4 there. How do I get rid of that 4? How do I deal with that 4? Well, what if I do this? Could I multiply top and bottom by 1/4? Is that a legal move, first of all?
Yes.
Yeah. So now I have, how about if I write it this way? I now have 1/4 times. Now, what do I have on the bottom?
4 times 1 minus
x over 4.
Yeah, all right, 1 minus a 4th x. Okay, so not really anything huge except 1 over 1 minus R. That's my R.
Huh.
Oh, can I do this? Can I do that? Stare at that for a moment. Am I matching it exactly? If this equals this, then all I need to do is have 1 over 1 minus R. I have 1 over 1 minus R at the end. Now stare at that for a moment. Is that a true statement mathematically? Well, as long as this is true, it is. Now, is this in the form of a power series? Exactly.
No.
Not quite, it's almost. The form of a power series is you have your AN and then you have your x to a power as separate entities. So what I just kind of need to pull that apart. Because the form of a power series, I want the x to the n to stand alone. Now, what's in front of the x to the n?
1/4 to the n.
1/4 to the n. Could I write it as 1 over? Would this be
4 to the n, yes.
Would this be more or less useful, do you think?
More useful.
It's probably more useful because then what about this 1/4 here? I'd like to.
And then you do an n plus 1.
N plus 1, perfect. This is the best answer I can possibly give. There's my AN, x minus 0, if you will, x to the n. Is this always true? No, it's true when?
R is less than 1.
So it's going to be true when 1/4 x in absolute value is less than 1. Now, when is that true? When the absolute value of x is less than
4.
4. Oh, okay. So for all real numbers, basically between -4 and 4, that quotient is equal to that sum. Isn't that crazy? Whoa. Now, I want the radius of
I'm not
convergence.
muted.
Make a lot of background noise here. I want the radius of convergence. Radius of convergence is a value. It's this inequality is a true statement. I'm going to converge everywhere this inequality is true.
So we just do same thing we did before with a -4 less than x less than 4. And then,
That's the interval. Radius
Oh,
is a
okay.
value. So radius, think of it this way, radius is easier. Radius comes first, and I can create an interval once I know the radius. When I drew the picture yesterday, I drew a picture on the number line. Now I'm centered about 0, by the way. And how far am I going in each direction? Well, 4. That's why we can say it's -4 to 4 is the interval. What's the radius?
Isn't the radius just 4?
8. Oh, 4. Sorry, 4. Yeah.
You think you think diameter. So does everybody understand the radius is the number 4? Where did it come from? It came from this. Oh, I'm within 4 units of where I'm centered about. So those words we used yesterday, centered about, is really important. Yes.
Why are you calling it a radius for a sum?
Well, the radius is how far I'm going in each direction to get my convergence.
Okay,
The radius of convergence. So
the
here's what we
radius
don't
of
know.
convergence. Okay,
Here's really the question. We just said that this is equal to this. Well, yes, but not for all real numbers. But let's just make it fun. What if you replaced x with 100? Then I'd be going 100, 100 squared, 100 cubed, 100 to the fourth. Wouldn't you say those numbers are getting astronomically large really, really, really fast? But if I put 100 in here, this is a tiny fraction. Tiny negative fraction, astronomically large number, probably not equal. Oh, this is exactly equal to this if I'm within 4 units of 0. Oh, okay. So only for this interval, -4 to 4. So my radius is 4. 4 units from where it's centered, and it's centered at 0. How do I know it's centered at 0? How do I know it's centered at 0?
Because it's just an x, not a plus
Yeah.
or minus with it.
Yeah, it's not x minus 3. It's just
Because
x
C is
minus
0.
You don't write
Okay.
x minus 0. It's just if I have x to the end, it's centered about 0 because that's equivalent to x minus 0. Now, was the algebra here difficult? No, it's pretty simple.
no.
So we're gonna do this a couple of
So-
times.
So the radius here has nothing to do with a circle.
Well, I'm glad you asked that question. It's kind of an odd term because we're on a number line. Agreed? We're on a number line. Radius is kind of funky. So I'm going to go back. That's, by the way, Nicola, that is an awesome question, because the only time you really deal with this concept is in epsilon delta proof, which is day 2 typically of Calc 1. And we use terms like radius and all that stuff. You say, why would I do that? Here's why. Okay, so guys, make sure you're muted because I have a lot of background noise. So I have the number A, and on the number line, we'd say a radius, and we usually use, by the way, we usually use delta, and we'd say that's A plus delta, and that's A minus delta. So think epsilon delta. So on the number line, it's that. But what if I was in 2 dimensions? Okay. Better yet, what if I was in 3 dimensions? In other words, it's an interval on the number line, it's a circle on the XY plane, it's a sphere in 3D, and it's the same radius. Does that make sense? That's why we use the word
Yeah,
radius.
that's
It's the same
awesome.
meaning radius. It's the exact same meaning, but it has to do with dimension. So if you're only in 1 dimension, there can't be a circle. So radius would only apply on the number line. If you think of a circle, what's the definition of a circle? It's the set of points on a plane that are equidistant from a given point. The given point is the center. That equidistance is called the radius. Oh, what's the definition of a sphere? It's the set of points in 3 dimensions that are equidistant from a given point. Oh, now I have the same radius, but now I'm going in every direction. So on a number line, the radius would be that I would only get those 2 values based on the radius. Circle, sphere.
Nice.
So it's a great question, But when we're looking at a number line, it's hard to understand why are we using that word, because we also expand it to 2 dimensions. We expand it to 3. In Calc 3, we do the epsilon delta, we do it in 3D, and now all of a sudden, okay, going, oh my God, oh wait a minute, I'm using the exact same vocabulary, I'm just in a higher dimension, and it kind of opens up. And I'm glad you asked the question, because we're not drawing a circle, but we still use the word radius.
So is it like it's
Oh,
the
that's
radius
awesome.
because we're looking at the circle, but not from a top view, from its sideways?
Yeah, if it helps to think of it that way. It actually, the where this comes from really is the complex number plane, which I won't really go over until you're in differential equations. But now radius is on the XY, but the XY plane is the complex plane, and I don't want to go there because your brains will hurt. Okay, that's too much information right now. When you're ready for that, it is some of the coolest stuff. And everything you've ever learned in your life changes when you throw in the complex world and you go, oh, that's what's going on. But when the time comes, the order of things, Calc 1 and 2, you master 2-dimensional calculus of real numbers. You don't use complex numbers in Calc 1 and 2. Calc 3 is you take the mastery in 2 dimensions and then you expand it to 3. So you just take your rules and expand them. You don't start over. So calculus 3 is now the mastery of 3-dimensional real valued calculus. Now, when you hit your upper division courses, you're going to take a course called complex analysis, which is the mastery of the complex calculus in 2 dimensions. You don't even bother with the complex in 3, you just do it in 2. And then everything opens up and you, oh my goodness. But you have to do things in order. We can't start with 3-dimensional calculus until we master 2-dimensional calculus. We can't do calculus of complex numbers until we master the calculus of real numbers. That's why we do things in a certain order. It's not watered down, no, but we got to get one thing at a time. So when you're ready for the next thing, it's because you have all the background taken care of. So that problem was relatively simple. Let's do one a little bit harder then. All right, what if I had something like this? I have x over 9 plus x squared.
Oh my gosh.
I want to write this as a sum. In other words, your goal is to write it in this form. That's your goal. Ew. Can I factor things out?
Just factor out the x.
So like, does that bother me? No, I can just factor it out. Does that bother me? No, let's just factor it out like we did before. Can I write, let's do that as the very first step. Now, what's on top?
1.
What's on the bottom?
1 plus x.
So I'm going to have a 9th x
Yes.
squared. It's
Sorry.
a plus, but I need it to look like this. I love some space. Can I
Negative.
do that? Is that legal? Well, are these equal?
Well, anything is legal if you don't get caught. So
I've read that in a magazine.
Are these equal? Stare at it for a moment, because I don't want to lose signs. Are they equal?
they are.
Yes.
Yeah, because minus the negative. So I have now written it in this form where very, very specifically that is my R. So that's the thing that's going to show up to a power in my sum. Now, you got to admit, this is kind of cool that I can even do this. What
But you
about
can-
this? This
Yeah,
goes
what about
forward.
this?
This is the summation. This is just multiplied. So I'm going to write it like this. Now, what
Oh,
am I
it's the
reducing to a power? The whole thing. Okay, we don't want to jump the gun. We'll do one thing at a time. Now, tell me about this particular series. Tell me something about this particular series.
It's a power series.
Alternating.
It's alternating.
An alternating power series.
Sorry. Yeah, yeah.
I'm so sorry. Is that an A or a 9?
It's a 9.
9.
Okay.
All right. So now what do I do? Well, it's going to be x to what power?
2n.
Okay, let's keep that outside. How about I put the -1 to the n on top and then over what? Over 9 to the n. Okay, you with me so far? And I still have that guy right there. Can I work this in easily into the answer?
Yeah, you can just like add it to the x part of it.
What's the denominator now?
81.
N plus 1.
9n plus 1.
9 to the n plus 1. And what's this term going to be?
X cube n.
No. What are the
X
rules
to
of
the 2n
exponents?
plus 1.
Add exponents at this point. Yeah. Cool. We just took that quotient and we wrote it as that power series. Now, is this always true? We know the answer. No, I have a restriction. And what is my restriction? What's the restriction? The absolute value of
Negative
-1/9 x squared must be less than 1. Well, the nice thing about the absolute value of -1/9, that would just make it positive 1/9. So can I say x squared is less than 9? Is that true? Stare at that for a moment.
Yes.
So the absolute value of x is less than
3.
3.
By the way, I dropped the absolute value because it's already an x squared, but it would be okay to have left it there. Oh, so if the absolute value of x is less than 3, then x squared will be smaller than 9. So -9th x squared in size would be smaller than 1. Life is good. What is my radius of convergence?
3.
3. If I asked for the interval
yeah.
of convergence, then you would basically say, all right, that's the true inequality. So the interval would be just from here to here. That would be the interval. Now, really simple question.
Professor, for
Yeah.
that interval though, we would have to do the test at x equals -3.
That's what I was about to say. Do
Perfect.
I have to test this interval? Do I have to test the endpoints?
We should be testing at least the positive, right? The 3, and then we also know that the
Yeah.
-3 would be.
How are we treating this? We're
As an
treating
alternating series, so you'd have to test the
Oh.
negative.
nothing to do with alternating. No.
No,
How are we
geometric.
treating this? We're treating
Geometric.
we're treating it not that it's asymptotic, that it is geometric. We are saying, no, this is geometric and this is my value of R.
Right.
Why don't you have to check the endpoints? Because it is geometric. Geometric series diverges at both endpoints automatically. So I'm off the hook. I don't have to check the endpoints. It can't converge at either endpoint. That's impossible because it's geometric. What we looked at the other day were things that were asymptotic. They acted geometric, so we still had to check the endpoints. This straight up is geometric. So that's nice. So now in this type of problem, because I'm centered about 0, to say my interval's from -3 to 3 and to say my radius is 3, I'm saying the exact same thing. So that's why in this problem, we usually just say the radius. It's less writing, it's less work, and it's absolutely clear because I'm centered at 0. If my radius is 3, then I'm just going 3 in each direction. If I was centered somewhere else and I gave you the radius, now I have to think about my interval, don't I? If I'm centered at 10 and the radius is 3, let's see, then that goes from 7 to 13. You know, I got to actually do some calculating in my head. Complicated stuff, of course.
So the answer to that question is just when we see it is going to be radius 3.
Well, it's going to be, this is the power series. And
Yep.
radius of convergence is 3.
Okay, so I write that whole thing.
Big,
Just-
big,
Mm.
small. This is our goal. This shouldn't trouble us, but remember, this isn't true for all real numbers. This is only true for a short range of real numbers, and that's what the radius of 3 is. So
Okay, I see.
really the rule is, if I got a quotient of things involving x's, if I can get it to look like 1/1 minus r, and I just did it here, I factored something out to make it look like that. Oh, even when the sign was backward, I just meant I had a negative here. We like this problem. This, you got to admit, this is kind of cool.
Professor,
Professor.
Before I erase everything. Okay.
Yes. In the middle, can you explain how to multiply x/9 with the summation for someone who like doesn't know?
Oh, okay. What's the only thing in the summation that's changing? Is the
N.
There's no n's here. So this x and this 9 are basically like constants because there's no n's. I could move things in and out as long as they don't have n's involved. Okay, so I have an x to the 2n, and I'm basically taking this and I'm multiplying it inside instead. I'm just moving it inside. Okay, so I have 9 to the n times another 9. I have x to the 2n times another x. That's it.
Well, then you add the exponent. Oh,
Yes.
oh, I see. Because it's 9 to the exponent of 1 and x to
Yeah,
the 1, 9 to the 1.
Yeah, that's the
Exactly.
safest way of thinking of that.
I also have a follow-up question before you erase.
Because the
first
first, because my first thought was to multiply the numbers, or when you get like x times x, you get x squared or.
Right, but I already have an exponent, so that's when I get to add them. So what's your follow-up
Okay.
Tom, before I move on?
So if we get a question like this with the initial part of what you had, which was the x divided by 9 plus x squared, and you ask us what the interval of convergence is, we don't even have to go through the whole thing. We just have to get to the 1/1 minus negative 1/9 x squared, and we find the interval of convergence, and that's it.
Well, are you saying, can you find the interval of convergence without the power series? Is that what you're saying?
Yes, I'm saying like
Yeah,
if you're going to
yeah.
ask us a question like this
Yeah,
of just
right.
finding an interval of
Yeah,
convergence.
you're never going to be asked for the interval of convergence without the power series, because the power
Got it.
series is the power series is the more important part. Like I said,
Okay.
this is why I say to Nicolette, big, little. So
Cool.
if this was an exam question, this would be 80% of the points, 20% of the points, because the power series is what we're going for. But the radius is important because we're saying it's not always true. I got a restriction and there's my restriction. But the restriction
Cool.
here was not hard to find. The only mistake people make is not the wrong radius. They just forget to do the radius. That's the only error everybody makes. I rarely get the wrong radius. I just don't get any radius. We kind of forget that sometimes. Now that we have this is a very, very specific problem that only applied when I have simple quotients that I can manipulate. You're not always going to have simple quotients. So now the question is, okay, I want to create a power series from a given function. Now, yesterday, what I did was I just randomly made up power series. That's what I did. I just made them up off the top of my head. I got a whole bunch of them stored up here. Okay. I just went ahead and deleted a bunch of phone numbers. And then, that's how I remember things. I have a limited storage capacity. So today I want to do something totally different. I want to start with a given function. And I want to create the power series that goes with it. There's an infinite number of power series. They don't all go hand in hand with a given function. So let's suppose that I have an f of x. F of x will be e to the x, or sine x, or cos x, or log x, or inverse tan x, square root of x. F of x is a very specific function that we've already earmarked and we've got. I know that this is equal to an x minus c raised to the n for some value of c and for some sequence of guys. I have to just figure out what they are, though. I don't know what they are, but I'm going to show you how to figure it out so that no matter what f of x is, I'm going to show you how to come up with the specific power series that goes with it. So now I got to give you a couple of definitions. These are words that you've probably never heard, but they're very important for what we're doing. The first one is called analytic. Analytic. And I don't know if I don't think I've posted these. I will probably post these in the lecture notes. Analytic has to do with being differentiable. Being differentiable means I can actually take the derivative. So let me remind you of some really simple things. In Calc 1, okay, we have a lot of functions that are continuous, but they may not be differentiable. Differentiable means I can take the derivative and then evaluate the derivative. So there are 4 types of non-differentiable points that we learn in Calc 1. All right. I'm going to do examples of each one. First one, absolute value, which we do not spend a lot of time on in calculus. But the absolute value function is not differentiable at 0. We have what's called a corner. So at x equals 0, that's my problem child. Okay, it's called a corner. I'm on a line with slope -1 in one direction. I'm on a line with slope +1 in the other direction. There is no derivative at 0. Okay, the second one, y equals the square root of x. And again, I'm looking at x equals 0.
Doesn't exist.
Why is this not differentiable at 0?
There's a hole.
No, f of 0 is, I mean, 0 is 0.
Okay.
Because
Well,
there's nothing to the
Nothing before it.
Because there you can take several tangent lines at the end.
Yeah, but first of all, there's no derivative at 0, because if I take the derivative, I'd have the root
This
x
would
in
be
the
left and right.
denominator. Ah,
Yeah,
so this one fails because it's an endpoint. You're not differentiable at the endpoint because there's nothing on the other side. Okay, that's the second one. Third one. Move over here, sorry, I'm not gonna run out of room. Third one, y equals cube root of x. I'm giving you the types. These are just the easiest functions. Now, you know what the cube root, excuse me, what the cube function looks like. The cube root looks like this. And again, at x equals 0, we have a problem. If I take the derivative, again, the x will end up in the denominator. I have a vertical tangent, not an asymptote. No, 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 this is defined everywhere. But if I was climbing a hill at one point, it's completely vertical. So the derivative does not exist at 0 here because it's a vertical tangent, here because it's an endpoint, here because it's a corner, and my personal favorite, x to the 2/3, or the cube root of x squared. Guys, remember this one?
yeah.
What's that called? You remember? It's a word.
Cusp.
Cusp. Cusps are cool, but that one does not exist here because there's a cusp. These are the 4 types of places that I can have a function, everything's happy, but I cannot take a derivative at those values. So for each of these functions, the derivative is fine everywhere else, but it doesn't exist. So we would say for each of these, the function is not analytic at x equals 0, because I cannot take a derivative at x equals 0. So analytic has to do with differentiability. Now, it has more to do with differentiability than just this, though. Analytic has to do with what's called infinite differentiability. So what do you mean infinite? For example, if I take the derivative of something, I get a new function. But what about the derivative of that, and the derivative of that, and the derivative of that? Simple example. I've got a function y equals e to the x. I want to differentiate this one time. I want to differentiate it 1,000 times. Do we agree that every derivative forever and ever and ever is going to be e to the x?
Yes.
Yeah. By the way, can you evaluate e to the x at every real number?
Yes.
Yes. So we would say this is analytic at every real number, because every derivative of this forever and ever and ever will exist, and it will exist at every real number. Cool. All right. How about something like x to the 3/2 power? Actually, let me change it. I want to make it so I can do positive. Sorry. X to the 4/3 power. Okay. This is defined for all real numbers. Okay, there's no problems. I can use negatives because I have cube root. This is defined and continuous for all real numbers. Now, the first derivative is 4/3 x to the 1/3. It's still defined for all real numbers. The problem is the second derivative. Excuse me. What's the second derivative? It's 8/9 x to the negative 2/3, or 8/9 to the 2/3. Does this ever have a problem? Yeah, it's 0. Oh, and every derivative I take forevermore will have an x in the denominator. Do you agree? So
Yep, 'cause-
every derivative I take forevermore will also not be able to be evaluated at 0. So this function and every one of its derivatives can be evaluated at every real number except 0. I run into a problem at 0 after a couple derivatives. So we would say this function is not analytic at 0, but it's analytic everywhere else. So it's the ability to take derivatives and evaluate them. So sine, cosine, they're analytic for all real numbers because I never run into issues. Things with quotients, I often run into issues because things end up in denominators. So where a function is analytic is where I can evaluate it about. So the rule here is this f of x has to be analytic at that number in order to expand it about that number. And here's the best part. That c most of the time is going to be 0. When it's not 0, it's going to be 1. You're never going to see anything else when you are creating your function. Okay.
So in other words, you're almost saying, well, you're saying that at C, the function is differentiable
everywhere. or-
infinite amount of times and is continuous at this
That
point.
means that this means that f of c, f prime of c, f double prime of c, f triple prime of c, forever and ever and ever, those always exist.
Perfect.
Most of the time c is going to be 0, which is happy. But in those that last example I did where I couldn't do 0, I would use
Yeah.
1. Because 1's an easy number to work with. Oh, okay. The natural log
Sold.
function. Not only is the natural log not defined at 0, but the derivative of log is 1 over x, and all of its derivatives will involve x in the denominator. So the natural log function is not analytic at 0, but 1's a perfect number to use because all my derivatives are happy at 1. You wouldn't use 7 or 130. You'd use a number that's easy to work with. So I'm going to prove to you how
Professor.
everything comes from. So
Yeah, I have a question too.
Professor, for the example you just did, you said that the x to the 4/3
Mhm.
is, well, my question is, do we call it, is it not analytic, or do we call it analytic for all real numbers except 0?
yeah, but
Or-
Yeah.
specifically, you
Same?
say it's not
Question.
analytic at 0. You're
But
saying-
it is analytic for all real numbers except for 0, right?
Exactly. So if this was the
Okay.
problem and I was trying to use x to the 4/3, I would probably use a c of 1 because it's convenient, but I couldn't use a c of 0 because the derivatives don't all exist at 0. Now I'm going to go ahead and show you this. So if I expand this, I want to do the first few terms for you, okay? So if I expand this, what am I going to get? Starting at 0, I'm going to get a0, a0 x minus c to the 0th power is just a0 plus a1 x minus c to the first power plus a2 x minus c to the second. I'm going to do a few because we're looking for a pattern here. I'll do this many because that's all I can fit. Okay. So everybody agrees with that. All right. Let's write the first couple of derivatives down now. What is f prime of x? Well, it would be 0, just a1 plus 2a2 x minus c to the first power plus 3a3 x minus c to the second power plus 4a4 x minus c to the third power. Okay, forever and ever and ever. Everybody cool with that? What's the second derivative? I'm just going to do a few. Well, that would be 0. I would get just 2a2 plus 6a3 x minus c to the first power, 12a4 x minus c to the second power, and then forever and ever and ever. There's a pattern that I'm hoping you all see in a moment. Okay, that's 0. That would just be 6a3. Then I'd have what? Plus 24 x minus c to the first power. Now, by the way, every other term has an x minus c to a higher power. Do you all agree? Because the next one's going to be 5th, 6th, 7th, 8th, 9th. So after this, every term has x minus c's to progressively higher powers. Let's do one more. Let's do f fourth derivative, in which case I could actually put a 4 now. 0. Now I just have 24 and then plus a bunch of things with c's. Okay. Sorry, 20. I lost my a to the 4th. Sorry. There should be a to the 4th. Or a4, sorry. There we go. 24, a4. I think I've got, yep. Now, here's what I want to do. I want to take each of these derivatives, and the function itself. I want to evaluate everything at c. And I'll do it right here. What is f of c? If I evaluate the whole thing at c, won't every single term here be 0? And what will I be left with?
A sub 0.
Just say sub 0. Okay. What's f prime of c? Evaluate every single thing here. Oh,
2a2.
well, these are all going to be 0, aren't they?
Oh yeah, sorry. A sub
No,
1.
you're
I was
looking
looking
at
at
my A1. All right. What's f double prime of
I
c?
see. So A2, A3, A4, so on, so on.
Okay. What's f triple prime of c?
A sub 3.
I said, we'll do one more because that's all I could fit on here. Huh. Here's what I'd like to be able to say. I talked about pattern recognition. Here's the first time we absolutely need pattern recognition. How am I'm supposed to see a pattern? Well, I think this is an easy pattern. Think of this as the 0th derivative, first derivative, second derivative. I think you see a pattern there. Do you think I'm gonna have an AN there? you think I could say that? Everybody?
Yep.
Yeah.
Absolutely.
Now what's the coefficient? 24, 6, 2. Do you see anything there?
It's times 2 times 3 times 4.
Isn't that 4 factorial?
Mm-hmm.
Isn't
Yep.
that 3 factorial?
In factorial, I see.
Factorial. Isn't that 1 factorial? And even better still,
Yep.
isn't that 0 factorial? So what goes here?
And factorial.
And that is, I would say, in your 1.7 semesters of calculus life, so far, this is actually, other than the fundamental theorem of calculus, the single most important result. Because this sets the stage for entire branches of mathematics that you saw that pattern, that the nth derivative evaluated at C is simply going to be n factorial an. Why is that important? Because that tells me what the coefficients are now. Remember, I said we have to figure out what an is. C, I know, that's given. I don't know what an is. I do now. Can you tell me what an is? Yeah, it's this divided by this. All right, I'm going to erase some of this because I need the space. So when I'm trying to create, it involves taking derivatives of this. I can now say this is equal to. This would be taking this and solving for an. This would be the nth derivative evaluated at C over n factorial, x minus c to the n. And remember what I said about c? I said most of the time c is going to be 0. This is why you have to be analytic at c, because I'm taking technically an infinite number of derivatives and evaluating every one of them at c. Oh, okay. That's why I have to be able to go forever and ever and ever with the derivatives. You're never going to go forever and ever and ever. You're going to go until you see a clear identifiable pattern, which you pretty much will always be able to. The nature of the problems we look at, patterns, won't be that complicated. This process to come up, to say that f of x is equal to this result is called a Taylor series. A power series is anything of the original form. The Taylor series is where I created the power series by doing this. Again, if everybody here just made up a random power series off the top of your head, it's a legitimate, meaningful power series, but it didn't come from anything. There's only a handful of functions that I create the power series from. So let's create e to the x, shall we? I told
The
you
Taylor series is a power series.
a Taylor series is a power series, but it's the power series that we created. Nobody told us. Yesterday, when we were doing examples and finding intervals of convergence, I was just making up random power series. They weren't equal to any particular function necessarily. Oh, okay. So let's take f of x equals e to the x. Now, what's f prime of x? Well, that's e to the x. What's f double prime of x? That's e to the x. In fact, I can do this for a while. And we want to expand about c equals 0. Why 0? Because e to the 0 is easy to calculate. E to any other number would be nasty, right? You choose the number to expand about out of convenience. So clearly, e to the 0 is easy. So with that being said, then f of 0 equals f prime of 0 equals ... equals the nth derivative. Every single, anything e-ish when I evaluate at 0 will always give me what?
1.
1. Now, according to what we just figured out, that's an absolute, that's a formula, that's a theorem, that's a law. For the expansion of e to the x, I want e to the x to look like this. My an is supposed to be the nth derivative evaluated at, in this case, 0, over n factorial. Didn't you just tell me that's always 1?
Mhm.
So that means my an is this. So I can now say e to the x equals 0 to infinity an, oh, it's x minus 0 to the n, isn't it? And that's how we come up with e to the x. It was actually this simple. It's this simple because we now had the form of a Taylor series. We can do this for anything. We can do this. We'll do it for cosine because cosine is a really simple one to come up with, and it's a very powerful one. This is an absolute. Now here's the best part. This converges for all real numbers. We showed that yesterday. When I do my ratio test, the ratio it'll actually be 0 when I take the limit. So this converges for all real numbers. There's no value of x that I can't use there. Cool. Okay. You like that?
Yep.
So a Taylor series, again, a Taylor series is a power series, but a Taylor series is one that we came up with. We just came up with this. We weren't told this. So what I'd like to do is come up with the Taylor series for the cosine function. I like the cosine because it does show up a lot. Now, cosine and all of its derivatives will just look like sines and cosines. Do you all agree? So do I want to expand those about pi over 4 or pi over 2 or pi over 3 or pi, or what do you think I want to evaluate all my trig functions at? What would be a really convenient number?
0.
How about
0.
Yeah, why not just stick
Yeah.
with 0? It would be, you could use any real number. Well, why would
And
you?
I mean, anything that includes like a 0, pi over 2, pi, 3 pi over 2, or 2 pi would be,
anything pi-ish would be correct, but now my power
Right.
series would be of the form x minus a multiple of pi raised to a power.
yeah.
You notice how
that
hard
starts-
that would be to work with. when you're
Sounds
trying to-
dirty.
Yeah, I don't want x minus, 4 pi. Because when I actually evaluated at different values of x, I have some really nasty, evil looking number.
Yeah, it's more just to like make sure we understand it properly.
So.
Makes sense.
Hold on a second. We're gonna do, let me write it this way. I'll do f of x equals cos x. So now let's take some derivatives. F prime of x, let me need more space. This process is not difficult in general, which is why I want to walk you through it right now so we really get it nailed down. F prime of x would be negative sine x. F double prime of x would be negative cos x. F triple prime of x would be positive sine x. F fourth derivative of x would be back to cos x. So does this pattern repeat itself forever and ever and ever?
Yes.
Yes.
Yeah.
So I can stop now because at least with the derivatives, I see a pattern, but it's not the derivatives. It's the derivatives evaluated at. Now we said we were going to use a value of 0. We don't say x is 0. No, x is my input. When I say cosine of a number, no, it's not x that's 0. It's c is 0 because c is a constant. X is a variable. We don't want to confuse the two. So we're going to use c of 0. So now what is f of 0, f prime of 0, f double prime of 0, f triple prime of 0, f fourth derivative evaluated 0. All right. So what are my numbers? Anybody? Rattle them.
Am I crazy? Cosine
One.
of 0 is 1.
1.
1, -1. Wait, is that sign? I can't see.
0,
Write them down or no?
Yeah, 0.
negative 1.
-1, 0, 1.
Can you tell me a pattern of the coefficients then? Do you agree that all of the odd derivatives are going to involve sine? Do you agree with that?
Yes.
Do you agree all the even derivatives are going to involve cosine?
Yes.
But those values are going to alternate. That's kind of interesting, but I got the zeros in the middle. So here's what I would suggest. Let's just simply write out the first few terms of the power series. So what the power series is, if I write out the first few terms, it's always going to be a0 plus a1. In this case, it's x minus 0, right? Plus a2x squared plus a3x cubed. This is what the power series is going to look like. All right. Now, what did we say before? We said that the nth term is This guy evaluated at C, which in this case is 0. So that means my power series is going to be A0 is going to be the 0th derivative. So it's just cosine, which is 1. So technically it's 1 over 0 factorial plus, well, isn't A1 going to be 0? So it's going
Yes.
to be 0 over 1 factorial x plus negative 1 over 2 factorial x squared plus 0. See what I'm doing here? That's the pattern. The factorials are always the denominator. X cubed plus 1 over 4 factorial x to the 4th. Now, this is what my power series is going to look like. Non-zero, 0. Non-zero, 0. Non-zero, I really want to get a general term, but I don't have any odd numbered terms. Let me know anything clever we can do. Let's see more. This is something I know, Tom, you know this from discrete math. Odd integers versus even integers.
Right. 2k.
Yep. For integer k, we know 2k is even and 2k plus 1 is odd. For any integer, if you take 2 times that integer, it's even. So what I need to do is write a pattern that involves only evens. Okay, so at some point, I'm going to have x to the 2n. And by the way, what factorial goes with x to the 2n?
And
Doesn't the exponent right now
sorry.
factorial?
Yeah.
Yes, sorry.
So does everyone see
And
that?
factor. And then you
So far, so
have
good.
an alternating series.
Negative 1 to the power of n.
Perfect. Because when n is 0, positive 1, I'm here. Here's the cool thing. When n is 1, negative 1, but it's x squared and 2 factorial, I'm here. When n is 2, positive 1, x fourth, 4 factorial, I'm here. Cool. So we figured it out. I can now say with absolute certainty, the cosine of x is equal to negative 1 to the nth, 2n quantity factorial, x to the 2n. That, folks, is extremely cool. You can do this for every function. The caveat is pattern recognition. Pattern recognition is not always an easy thing, but one of the best parts about Taylor series is you don't always have to do the whole thing. You might only want the first few terms. For example, last day I did the thing with the sine x. Remember, I graphed it on the graphing calculator and showed you how close it was. What if I wanted to do the same thing with the cosine x? Could I literally just graph this on my graphing calculator? Can I just do that much? And this is something, if you have a graphing calculator, I really would like you to try this on your own. We need to get rid of this. I can do this, but when I'm showing it, it doesn't translate quite so well when I'm holding it up. So if I said, consider y equals 1 minus a half x squared plus 1 over 24 x to the 4th. Just consider that much only. If
I
you
have a
graph
quick
this on your
question.
graphing calculator, it's going to look like a cosine graph for a while. Yes.
So for Taylor series, what is the interval? Is it for all real?
Well,
No.
that's the thing. It's not automatic for everything. I would have to now do the ratio test. But when I do the ratio test on this one, there's nothing on top. There's the 2n factorial on the bottom. The ratio test on this one, when I do the limit of the consecutive terms, again, it's going to be 0. This is going to, again, converge for all reals. Sine, cosine, e converge for all reals. They're wonderful. Log, not so much. Log's a little trickier. So let's do a different one now. Okay. There's only a couple more things I got to get through today. I want to show you how to do a Taylor series. You do not have to memorize the results. If I ask a question, I'll often say, here's the power series or the Taylor series for cos x, and then you'll do some stuff and some tweakages. That's kind of cool. Here's what I'd like to do. If I only write the first few terms, in the last case, I just did, sorry, I erased it. I just did, we'll call it P4 of x. That means the fourth degree polynomial. We said it was 1 minus a half x squared plus a fourth x to the fourth. That's a fourth degree polynomial. Agreed? This is called not a Taylor series.
And Professor, that's a 4 factorial.
Oh, thank you. Thank you.
Yeah.
I actually wrote 24 last time. Yeah, thank you, Tom. This is called a Taylor polynomial. Why? Because a Taylor series is infinite. I just wrote 3 terms. That's not a series. That's a fourth degree polynomial. But here's the coolest part. If I'm close to 0, now why do I have to be close to 0? Because we're expanding about 0. That's why you have to be close to 0. If we'd expanded about pi, then I have to be close to pi. You have to be close to whatever the c is. If I'm close to whatever c is, then this will look like a cosine graph. It's crazy. Meaning I can say this, that P4 of x is asymptotic to the cosine function. I mean, that doesn't even make sense at first, but if I take small values of x in radians, by the way, if I take small values of x and I evaluate this and I evaluate this, my calculator is going to show me decimal values that are almost identical. It's crazy cool. Because then that leads to a lot of really, really good calculus things. So the Taylor polynomial is a finite number of terms. The best part about Taylor polynomials, you just have to write the first few terms. You don't actually have to see a pattern if you're just doing a few terms. So let's do an example. I want to use f of x. I'll do something terrible. How about 1 over the cube root of x? Now, what we want to do is I want to get a Taylor polynomial. I don't want the whole Taylor series. I just want the first few terms. So we're going to find, first of all, P3 of x. That means the third degree Taylor polynomial. There are no roots in the Taylor polynomial. Now we want to estimate, let's say 1 over the cube root of, how about 1.1? I want to estimate this with my polynomial. I'm going to show you the value of this. Now, yes, so I have a calculator, I can do this. That's not the point. At the end of the problem, we'll compare the calculator value with our estimation, but I'm going to show you that there is a polynomial. Now, 1 over the cube root function, that's not a polynomial. That doesn't look anything like a polynomial. There's a polynomial that thinks it's that. Because they're going to be so close together.
Just the last part, because I was writing stuff down. What did you mean at
You cut
So
out.
you got cut off. Tom, we can't hear you.
Oh, well.
Okay.
hello?
You back on?
I think so.
You're back.
Sorry about that. I was just writing stuff down.
You got cut off again.
Dude, you're muted again.
Okay, I should not be muted anymore. I clicked the button. I'm
Okay, anyway.
estimate of 1 over the cube root of, what is that at the end?
Cube root of 1.1.
Okay, thank you.
Now,
Sorry, guys.
we're gonna start the process of the Taylor series, but we're only gonna do a few derivatives because we only need the third degree polynomial. We're gonna start the process. Then we're gonna evaluate the polynomial at the appropriate value. Now, the thing is, what should I expand this about? Because I can't expand it about 0. This is not analytic at 0. Obviously, I can't evaluate this or any of its derivatives at 0. So what would be a really good number to use instead of 0?
1.
1. Yeah, cube root of 1. I mean, yeah, 1 is the no-brainer. I would be hard pressed. In fact, I can't come up with a single example where you would use a number other than 0 or 1. I've never run into one. Textbooks will actually do this as an exercise. Okay, now do e to the x for, c equal 5, just random numbers. That's a waste of time because it's never going to come up. But 1 is what you use when you can't use 0, usually. So let's do the first couple derivatives. So we're going to use a c of 1, so we don't forget what we're evaluating at. So let's rewrite f of x, how about, as x to what power? Just so we don't possibly mess this up.
Negative 1/3.
The negative 1/3. Then the first derivative would be negative 1/3 x to the negative 4/3. The second derivative would be 4/9 x to the negative 7/3. And the third derivative will be negative 28 over 27x to the negative 10/3. Now that's all I need because I'm doing the third degree and that's where the derivatives show up. Now I'm going to evaluate each of these at 1. So f of 1, f prime of 1, f double prime of 1, f triple prime of 1. By the way, I do have posted lecture notes on this very specific topic right here. And I think I used a similar function. I used a square root or a cube root or something, just so it looks kind of familiar. f of 1, 1. Here's why you like 1. What's f prime of 1?
Negative 1.
I don't have to calculate it because that's 1. 4/9. Negative 28 over 27. Oh, okay. So I now want to write my Taylor polynomial, and that's where we use the p with the subscript. Okay. Third degree Taylor polynomial, we use a subscript of 3. The 3 does not refer to the number of terms. It refers to the degree. That's very important. So P3 of x, okay. So it's going to be 1 plus negative 1/3 over 1 factorial. I can write over 0 factorial. That's kind of redundant. Times what? Times x? Times x?
Times x minus 1.
X minus 1. Perfect. Because it's always x minus c plus. Now the second derivative over 2 factorial x minus 1 squared. Plus, I always write plus. I'll worry about the signs later. I just want to make sure I get the right terms in there. Now, if I don't do anything else, I do want to simplify those quotients, obviously. This is a third degree polynomial. This is a cubic. And I'm claiming this cubic is going to look ridiculously close to 1 over the cube root function, close to x equal 1. Not close to x equals 0. I got a vertical asymptote x equals 0. Now, I would like to simplify this if possible. And I don't mean multiply out the x minus 1s. I mean the quotients. So how about 1 minus 1/3 x minus 1 plus 2/9 x minus 1 squared, 28 27ths over 6. What would that be? And again, you can use your calculator. I'll just use my fraction key. 28 27ths over 6 is 14 over 81. I want to get it right. So minus 14 over 81, x minus 1 to the 3rd power. This is my P3 of x. This is the thing I'm going to tell you is asymptotic to this function. It's not equal, but for all practical purposes, if I use a value close to 1, would you say that's close to 1? Yeah. 1.1, then this value and this value evaluated at 1.1 ought to be really, really close together. Okay, that's my whole point of this problem. Let me.
Sir, I've been meaning to ask, why did we, in the beginning, the question was find P3 of x, estimate 1 over the cube root of 1.1. Why did we pick 1.1?
I just picked a value close to 1.
Why can't we use just 1 then?
That is 1.
F of 1 is 1 and we'd be done and really nothing to estimate.
Oh, okay.
Yeah, well, picking 1 would have been a little too easy, right? Now, do you know 1 over the cube root of 1.1 off the top of your head? No, but you do know 1 over the cube root of 1 off the top of your head. That's just 1. So I picked a value close to 1. There's no possibility you can calculate this in your head, but we can use our calculator and compare. So let me erase a little bit above here so I can squeeze. So we said that the cube root, 1 over the cube root function is asymptotic to this polynomial. Here's the way we say it. Oops, sorry. 1 over the cube root of 1.1 is going to be estimated by P3 of 1.1. They are not equal. That would not be possible. It would take the infinite sum to get equality. And what is this going to be? Well, everywhere you see an x, replace it with a 1.1. Well, what's 1.1 minus 1?
It's 0.1.
This is 0.1 or 1/10 if you want. Oh, so this will be 1 minus a third, all right, times a tenth. Plus 2/9 times what? Times 100th?
Yep.
Minus 14 over 81 times 1,000th, which I actually can write this as a fraction. I actually want to do that, okay? Oops, one, with a cheap calculator.
And that should give us an estimation of what the cube root of 1.1 will equal, or 1 over that.
Exactly. All right, so let me write this down. With my cheap calculator, this is equal to 78,466 over 81,000. Yeah, I can reduce that a little. I just common denominator made it easy. Okay. This could be estimated by this. Now let's compute the actual calculation there, okay? So my estimation, my calculation would be 0.96871 forever and ever and ever. Okay. The polynomial evaluated at 1.1 is equal to this, which is approximately this. Now let's compare it to the actual value. This will tell us just how good. Remember, we only did 3 derivatives. We didn't do infinity, we did 3. I mean, we barely even scratched the surface. All right, so what is 1 divided by the cube root of 1.1 equal to? My calculator says this is approximately 0.9687293, blah, blah, blah. All right, how good are we? Using only a third degree polynomial.
Can I ask you a question, please?
Yeah, looks like we agreed about 4 terms there. Or 4 decimals, yes.
So you wrote the equal sign in the first blue writing here. You wrote the equal sign when you were taking a value that's not exactly your fraction.
Just for the p-value 3. That's why.
No, I know. That's not my question. So when you write that equal sign, we can't use the squiggly lines to say
that's something else. This means asymptotic. When I'm doing a decimal, you would never use this if you're using this, because that's called an approximation. Approximation and an estimation, or asymptotic. No, if I'm using this and I got some infinite hideous decimal and I got to round it off, that's what the definition of an approximation is. I'm actually doing a calculator.
I see. You put it up there.
Different symbol, different symbol. Now, here's where it gets kind of weird. This is an approximation of this quotient, but this quotient is an estimation of this. Why? Because I'm using a polynomial that isn't equal to the curve. But by the way, guys, what do you think? We did third degree. We did 3 derivatives. Would you say that's pretty darn close?
Well, yeah, but this is cool and all, but was this like invented before the invention of calculators? Because it seems to me that this is kind of useless with calculators around, you know what I mean?
Oh,
1715. Sure. Yes, before calculators greatly.
Sure. Yeah, you said, but the point being that I'm demonstrating to you that the polynomial is absurdly close to the function. Now, why would that be important?
Why?
Physics.
Because less than 1 out of a million integrals have antiderivatives. And because as engineers, you're only going to be calculating definite integrals, and most of them don't have antiderivatives, you're kind of in a quandary. So how do you do a definite integral that doesn't have an antiderivative? You convert the function to its Taylor series. And you integrate.
Oh.
That's the most important thing you'll ever learn the rest of your life in calculus. That's what's used at every level. That's all of statistics is based on this. Any upper division engineering class is based on this. You can't integrate things in general, but you can integrate polynomials easily. And a power series is a polynomial. So I'm demonstrating to you how close together these are. Oh, heck no. If I want the 1 over the cube root, I'm using this. but I'm showing you how absurdly close.
Well,
it
that's,
is.
I mean, yeah, I'm not trying to be a smart ass. I'm just trying to
no,
ask, like,
no.
when they were working on this, were they trying to find the cube
Remember,
root, or were
remember
they
when
trying
we
to
were
find
coming up
something
with
else?
this a few hundred years ago? These are still a few hundred years away from being invented. So they
Yeah.
didn't have the ability to do the large scale calculations that we do. Now, here's the last thing I'm going to show you. This is sort of the crowning jewel of today's stuff. Because ultimately, I want to be able to do really gnarly problems without having to work extremely hard. I want to be able to answer questions seamlessly and easily, but most questions that come up aren't easy to answer if they're actually meaningful questions. So let me go back to this. E to the x, we know that you're going to love this. This is one of the absolute coolest parts of a Taylor series. We know this is true. This is an absolute. This is absolute. So if I wanted the Taylor series, or just say I want a power series, let's say for e to the 2x cubed. If I do this as a Taylor series, that means I have to take a whole bunch of derivatives, which I can do, but after the first derivative, it's product and chain rule. Everybody got that? It gets really big, really ugly, really fast. But I'm going to take a whole bunch of derivatives, evaluate all my derivatives at 0, figure out a pattern, and eventually write it down. That's absolutely correct. But there's an easier way. See my point? This is one of the best aspects of Taylor series. Once you derive your Taylor series, it's now subject to tweakage, as I call it. That's my mathematical term. We're tweaking it. So now can I clean this up a bit?
Mhm.
So let's see, 2 to the n over n factorial x to the 3n. Would you say this is still a polynomial?
Yes.
Can you differentiate and integrate that polynomial rather easily? Yeah.
Yes.
All right.
For Professor, I understand everything perfectly, but for those people who are confused,
Nice segue.
thanks.
Wow, Tom.
For those other people who are not
for the
me,
minor brains among us. Okay,
yeah,
what
for
did
the
Oh my God, Tom.
Anyway.
the summation here. So what are we using that for? I know this is an awful question. I'm just
Well,
trying to piece it together here.
I know my transcendental function is equal to this series. I know that, and I know it's going to converge for all real numbers.
Mhm.
I'm going to show you a little later, not today. I'm going to show you a little later how to actually integrate a power series itself without integrating a whole list of polynomials. There's a way you can integrate just the nth term. It's kind of cool. So here's where I'm going to leave you with this, because this is where we're headed next. Oh, by the way, I would really like to do the integral. Let's just say from, I don't know, arbitrarily 0 to 1. We'll just make up any limits. Doesn't matter. I'd like to do this. No big deal, except this has no antiderivative. So you could work the rest of your life, and there is no technique to finding the antiderivative. In other words, I just asked you an impossible question. This cannot be integrated, therefore it can't be evaluated. Darn, unless I integrate this instead. And I evaluate that result from 0 to 1, which I'm going to show you how to do, and it's utterly trivial, and you can get as many decimals as you want.
Okay, so this is what it's going to be for, because right now I'm looking at this and I'm kind of understanding, but at the same time, I'm not, like, all the things you're explaining about the practical application, I'm just blanking out on because I'm not really seeing
By
it
the
yet.
way, it's a saturation. We're done. I've
Got it.
posted a plethora of notes that takes everything we did into more detail, so that when you have time to look it over, probably wait till the weekend, focus on other things first. You look it over and go, okay, I see this. Here's sort of the big picture. Integration is going to be a very, very common tool to solve problems, but you can only integrate what you know how to integrate. What if you can regularly run across things that can't be integrated? They involve sines and cosines and e's, which, by the way, the farther you go in math, everything's only going to involve sines, cosines, and e's, and maybe polynomials. You see the same things. But if I'm doing things And I don't know what, I can't do that. Or worse, I just want the general antiderivative. Yeah, go ahead and go to Wolfram and ask it for the general antiderivative. You're going to get a hideous complex answer, but you won't get the right answer because it can't be done. But if you do this, you can get an answer because you said it's equal to this. Now you said, but wait a minute, I have an infinite sum. Yes, but if I take the Taylor polynomial that I know is asymptotic to the function, all I have to do is look at the first few terms. How many terms? It all depends on what you're doing. Okay, but it's so cool because I can do, and I'm going to show you this with the lecture notes. I can do huge problems with incredible calculations. The cheap calculator in my hand.
Yeah, because I know in my head that the Taylor series, I know that it's incredibly important, but right now I'm just not understanding the,
Yeah, this is day one.
significance
This is
yet.
day
Yeah.
one. Yeah,
Cool.
wait.
Okay,
There's let it. Yeah,
understood.
gotta let it soak in. This is
Okay.
the one disadvantage of our format, the every day per week.
That's why I'm worried.
In a normal semester, when I bid you all adieu, I wouldn't see you for 5 days, and you've had time to marinate in this. And okay, I got this. Now I see you in 8 hours or something. Anyway, let me go ahead. I want to talk a little bit about the exam, the general, just in case we forgot, because the question comes up. It's a valid question, although it, with the schedule, it's not a great question because the last exam ended with the integration, right? Miscellaneous substitutions was the last thing. So everything integral was the last exam. This exam started with limits and then L'Hopital's and so on, and ended with alternating series, which was, of course, today's quiz. Everything in that range is fair game. So that's 8 lectures. You're not going to be asked any question from the first exam. So there's always that, that feeling of, well, might I have to do another center of mass or solve a differential equation? No, on the final exam, you may see you will see some of those questions again, but on this exam, it'll only be from the 8 lectures, basically limits / L'Hopital's rule, improper integrals, and then convergence and divergence of series. So over and over and over again, same sort of theme. The exam itself, I was able to construct an exam where I asked you every single thing that I could possibly ask you, and then I'm only asking you to do some of those. So everything I could possibly want to see, I've represented, but you're not going to do all of them. You're going to do like 12 problems, not 50. But what I've done is I've carefully created an environment where, let's say one page is improper integrals, and the next page may be sequences. And the next page may be limits / L'Hopital's rule. That's all the questions on that page. You have to do a problem on every page. You don't have to do every problem on every page. You have to do a problem on every page, meaning you can't completely skip L'Hopital's rule. You can't completely skip, improper integrals. So I've asked you several of each thing, and you got to do at least one of each thing, and then 12 overall. The majority of the problems, probably close to half the test, is going to be series. And what most of you are going to do, most of you are going to do most, if not all, the series, because that's probably the most comfortable, because it's also the most recent. Like always, as long as you do the minimum number I ask of you, check your answers, then go to the extra credit. I ask you an extra credit, try the extra credit. And if there's time on the clock, go back and do some insurance. It is always wise to do insurance. So you made sure you did at least a problem per page and you did the minimum number of problems. So now when you go back and go, maybe it'd be wise for me to do a second problem on some of these pages, just in case my first one wasn't so great. Now that's just good planning. What's not good planning, let's say I give you 3 problems on every single page and you do every single problem on every single page and you never get to the series because you used all your time up. That's not good planning. So do every problem you can do, but don't do every problem on the test. You're not going to have time. It's, I've asked you to only do around half the problems I wrote down. Okay. So now in terms of formulas and things of that nature, unless you're doing an integral test, you're not really going to be integrating at all. And the integral test usually is going to, by the way, there's 2 possible integration techniques. I was going to say one. There's only 2 possible integration techniques you'll ever see on an integral test, and we used them both. Anybody remember what they are?
Isn't it just integration by parts?
Or the most basic one of all?
U sub.
That's it. Those would be the only, there's nothing else you could possibly run across.
No
And
evil drag?
Not on these, no. I know. I think I created a separate test for Yaman where it's just like
It's all
series
evil
of
trig.
right? L'Hopital's of evil trig. No, there's no evil trig on this one. And there's not going to be summations with trig stuff in it. Sorry, Tom and Daddy. You know, I know you guys want to.
I was wondering. I got scared last night. I was studying, and I was like, "Damn, I haven't done any trig stuff." Because
No,
of
not on this test. It's just not really part of the thing. Now, in terms of formulas, there really aren't much in the way of formulas, but there are a few rules. For example, most of the stuff was probably related to things like geometric series and such like that. So yes, it is true that a significant amount of the geometric stuff you would have learned in an algebra class, but because we presented it as if it was brand new, you know, so something of this nature. Let's say that this is kind of the textbook approach to this problem. They usually start at 1 and put an n minus 1. It's not any different. We know this equals a1 over 1 minus r if the absolute value of r is less than 1. Agreed? We proved that. You can write this down. I mean, we did a limit. We did a major proof of that. I don't need you to memorize that off the top of your head. You know, write that down. Ratio test. Limit as n goes to infinity of a n plus 1 over a n greater than 1 diverge, less than 1 converge.
So Professor, that was my question. I wanted to
That's a
put this,
theory.
I have a set of note cards with just my tests and like with the rules for them. I'm good to put on
Yeah,
a note card just less than
yeah.
1 greater than.
The only thing you can't do, you can't have an instruction step by step. Okay, do this, do this, do this, and you know.
Yeah, no examples or anything,
and,
right?
Because at that point it's open book, open note, and you're kind of off the hook for now. Over the years, my colleagues go back and forth on this one. It's very interesting because some of the folks I know, I hear you let them use formulas. I never do. And then I find out later, no, they let them use more than anybody. They just want to give the illusion that they're tough. Over the years, it's not even about whether you use formulas or not. I've had classes where I said, no formulas. I've had classes where I said, you can write anything down. And the funny thing is the results really aren't any different. The class that do not give formulas, believe it or not, tend to soar just a teeny bit higher, but it's not statistically significant. But what I see are the stress levels. The group that does not get to bring formulas tends to be way more stressed out because they're trying to do a lot of rote memorization in the process. This is not about rote memorization. That's why I say, write down the formula, just, you know, that way if you forget, oh God, was it greater than 1 or less than 1? You know, I'm blanking out. Most of you won't even refer to it because it's the writing it down that reinforces things for you. Okay. And again, I want you to be able to move smoothly through this. I don't want you to worry about getting every detail of a memorization of a formula because there really aren't formulas per se on this one, but that's a theorem, right? That's a theorem that we proved. And so that's a good one to do. The integral test, remember I said we bounded the series between the integral and the integral plus the first term. Therefore, the behavior of the integral. If the integral converges, the series converges. The integral diverges, series diverges. There's a theorem involving sequences.
Wait, please don't erase that yet. Oh, shit.
This is recorded.
Okay, you're right.
So the limit as n goes to infinity of a n equals 0 and a n plus 1 is less than or equal to a n for all. And remember that this just means at some point terms are getting smaller. That's called the nth term. If I fail the nth term test, I diverge. There's nothing else.
It diverges.
If I have an alternating series and it passes the nth term test, I get the very least conditional convergence. Ooh. So
Professor,
these are the kind of things you might want to write that down because that's major theorem stuff. I don't need to write an example to get that down. Yes.
Professor, for alternating series, I think I heard you mention that you only require the nth term test. You're not going to bother us with, you know, proving that it's decreasing, or is that something we have to do?
I said basically, this is part of it. But it would be darn difficult for me to find a problem where this passed and this failed. And by the way, does that problem exist? Yes, it does.
So on the exam, my question is on the exam, do you want us to prove it?
That problem exists, but it's exclusive to trig functions. Only trig functions can be approaching 0 but not be decreasing. It's crazy. So no, I said, I'm gonna just have you do this one. I'm not gonna let you, have you worry about that one.
Good
Because
question.
that one actually can be really challenging.
I mean, it's usually just, you know, 1/n plus 1 will be less than 1/n. That's usually how it goes.
Yes, here's the problem with that. The n plus first term, because I have n's on top and on bottom, trying to show this for this one is actually gnarly.
Tricky.
It's
Okay.
not trivial at all. And that's why I'm saying, I'm going to let you off the hook on this one. I know that's watering it down a bit, but let's face it, I'm never going to ask you a question where this succeeds and this fails, because that question only really exists if this is a trig. And I'm not going to ask you summations of trig in general. So that's really off the reservation. All right. I do want to take a break and do general questions, but I was just trying to prepare for the exam. Again, I will email you the exam a little bit early, just so you have time to print it and get everything, all your ducks in a row. I will send you the link and all that. Do log on immediately after you get the test. And then I just check everybody off. Don't really think there's anything else from a logistical standpoint. Nobody has to take it early. Thank you. Last test I had, actually, I think I had 4 people between the classes take it early last time. You said, what's the big deal? That means I had to give up 4 to 6 hours of my free time and do Zoom completely separate to sit there and stare at people taking a test. That's not the worst thing in the world, but I don't get a whole lot done at that point. So thank you for not asking this time around. Anyway, let's take a short break. I will stop recording now.